Welcome back. This is the third video in showing how to solve the process synthesis problem using ProCAFD. In the second video, we have used the example and set up a problem where we want to produce cumene from propylene and benzene. So now let's move on to the next step called as mixture analysis step. So once the user has set up the problem, he has to select this button called as the next step to move forward. So once the user selects the button, as you can clearly see, the program is trying to parse all the data given by the user, and it's trying to generate useful information to solve the synthesis problem. Here the user has to actually give a good 1 or 2 seconds time so that this analysis is completed. So now the program has completed the analysis, and all the analysis is divided into 4 different blocks here. The first one is the mixture analysis report, where it tries to generate or rather estimate the mixture condition at the given temperature and pressure. And the next is this analysis block, where the user has 3 different options to see. And the first one is the AZ analysis, and here the AZ refers to azeotropic analysis. First, it takes all the components present in the system, and then it generates all the different binary pairs available. Since we have like around 5 compounds, the number of binary pairs we get is around 10 binary pairs. So for each and every binary pair, it estimates the VLE, and it also estimates whether there is any azeotrope present in the particular binary pair or not. And apart from that information, it also gives you what is the maximum amount of driving force available to separate that particular binary pair or that particular binary system. So here the user has also the option to see the driving force diagram for each and every binary pair. Now let's select the driving force between cumene and benzene here. So the driving force is the maximum driving force available to separate benzene and cumene is around 45-46, while to separate cumene and disisopropyl benzene is close to 32 and 33. So, and those information can easily be seen here. The C and D refers to benzene and cumene, and we have maximum driving force around 46.35, while cumene and disisopropyl benzene is around 33.8. So what does this information gives to the user is that if you have a mixture of benzene, cumene and disisopropyl benzene, it's very energy efficient to separate benzene first and then separate cumene and disisopropyl benzene. So apart from these both analysis, the user also will have access to eutectic point analysis, where each and every binary pair is subjected to eutectic point analysis to find if there are any eutectic points available or not. So that's with this analysis block. And the next one is the binary ratio matrix, where for each and every binary pair, pure component properties are taken from the database, and a binary ratio of all the properties are estimated and some are shown to the user here, like the melting point, boiling point, solubility parameter, etc. So all this information, both the mixture analysis report, the azeotropic analysis, the binary ratio matrix, are used to generate the feasible separation techniques for each and every binary pair, which can be seen in the fourth block. Here the user has an option to remove if he thinks he doesn't require it, or he can even add based upon any laboratory data also. So that is the mixture analysis step in ProCAFD. Now let's move on to the next step called which is process group selection. So for that, the user has to select this button. So once I select this button, you can clearly see that all the information has been translated from the mixture analysis into the process group selection. Here, the process groups are the functional groups which will be used in the further steps to combine them and to form different flowsheet alternatives. So here, since we have given one raw material stream with propylene and propane, we have one inlet stream here, and the other inlet stream is pure benzene, so it will be given as IC. And similarly, we have defined 4 different process outlet groups in the process definition step. And apart from that, from the reaction analysis, it has estimated that we require a reactor process group, which has an outlet with all the five compounds. And further, it also has taken all the feasible separation techniques, and based upon that, all the different process groups are initialized with different components and are listed here. So what the program does is like it uses all this information in the further steps to combine to generate feasible alternatives. So these are the statistics for all these process groups can be seen here, where it is that the number of inlet and outlet process groups are in total are 6, and the total number of separation process groups available are 148, and the reaction process groups is 1, and with the total process groups are around 155. Now this step has another sub step where we gave options to the process to the user, where he can select or remove different process groups for the further for generation of alternatives. Here we can remove or all the membrane process groups, or we can only select the process groups with respect to distillation, etc. And these the solvent process groups, and these will be highlighted when we encounter any solvent based process groups like extractive distillation or liquid extraction. In that case, one can actually select different solvents from the solvent database here, and you can and we will be seeing different solvent process groups here. Okay. Now in the next video, I'll explain how these process groups will be used to generate the alternatives, and further how can the generated alternatives will be ranked.